The title of this talk, Small is Beautiful, is taken from a book that was published in the early 1970s by Ernst Schumacher. So Ernst Schumacher was an economist. He gave us what we effectively call environmental economics. He really started this view of a more environmental perspective on how we deal with resources. Now, what has that got to do with software? Well, a few things. I'm not going to talk about an ethical perspective. I'm going to talk about the fact that he is arguing against what we might consider the economies of scale. And he was talking about this from a physical point of view. Rereading the book, it's quite delightful because there's a whole load of stuff in this. It was written in the 1970s. There's a whole load of stuff. We're now living in the 21st century that he was looking to. It turns out we don't have quite as many people on the planet as he expected. We haven't quite reached peak certain resources, but we have gone beyond certain things that were not anticipated in the 1970s. And we've done some things well, and we've done some things very, very badly. So there's an interesting historical perspective. But his insight on scale and his philosophy, I think there's a lot that we can take with us. So the subtitle of this book is A Study of Economics as If People Mattered. The observation about an internet unique name, Kevlin Henney. My parents were very clever. They chose that before the internet existed, which is an amazing foresight. I actually did that for both my kids when they were born. I did Google their names to check that their first and last name combinations were unique, and that has paid off. My oldest son is now on Twitter. He's now 14, but last year he was saying, "Dad, what shall I use as my name?" Because all his friends are kind of like John Smith 1, 2, 3, 4. And I said, "Well, just try your name." And he's just like, "It's available." There you go. That moment was 13 years in the making. Okay, so you know, if you haven't got kids yet, think about this. All right, give them a gift. All right. However, I want to talk about code as if people mattered. And I want to talk about code as if economics mattered, because I think a lot of the time we've been working on this bubble that software is just getting bigger and bigger. Oh, there's failures, there's things that don't work out, there's companies that fold. But because there's so much money coming in, it's never really contracted. In all other industries, there's been a period of contraction and consolidation. Software has not yet experienced that, so everybody's still going around with startup crazy and so on. And so actually, economics of software is not something people are really worried about. They talk about it occasionally, but they don't really worry about it, which has had some problems and caused some problems for us. So I'm going to start off with this observation. It's the one I use whenever I'm talking about agile development, whenever I'm talking about software craftsmanship, whenever I'm talking about coding techniques, because this outlines a rather good goal. This is from the Brundtland Commission, the Brundtland Report given to the United Nations in 1987. It's a direct consequence of Schumacher's work. Gro Harlem Brundtland was the former Prime Minister of Norway, and she headed this commission, which gives us a really nice definition of what sustainable development is. Now, of course, they're talking about sustainable agriculture, sustainable economies, but it turns out the wording used here applies to what we want to do every day in our software. Sustainable development is development that meets the needs of the present without compromising the ability of future generations to meet their own needs. The problem is in software, a lot of the time we end up trying to meet the needs of the present and compromising the next release, basically. It's like, okay, we've got a deadline. Oh, well, don't worry about quality. Everybody work really hard, write lots of code. And that's the worst thing that can happen. People do. Yeah, there's that towards the deadline code. There's that feature, it must exist code. And then you spend the next few months, even years, dealing with the consequences of that mad rush. Okay, so there's loads of examples of that. There's also the other side of this, and I see this in some larger organizations. They never meet the needs of the present because they're so worried about the future. It's just like, oh, this will be really great when it arrives. When's it going to arrive? 6 months. You said that 6 months ago. Yeah, but we've got this framework, and we're now wrapping the framework with new middleware that we've developed, and we've got the middleware guys, and the upper middleware, and the underwear, and the lower middleware, and the lowerware. And it just becomes this complex arrangement of possibilities that never become real. So this is what we want from this stuff. And he says, for every activity, there is a certain appropriate scale. I like this way of thinking, Because the way that people go about software development, there is the idea that, oh, well, you know, we're a 100-person company, so we need to create software that's about that size. Or the last time I worked on a system like this, it was about this big. We had this many teams, and they were distributed across this many countries. So let's build it like that again, even though that didn't work out last time. Maybe we should make it bigger. That's what we need. We didn't make it big enough. We didn't have enough people. We didn't have a big enough budget. And that's exactly the wrong way. Okay, first of all, we need to step back and say, well, how big is that problem? What is the appropriate scale for this? And it turns out that the appropriate scale is often a lot smaller than we anticipate. Our experience has misinformed us. I'm from the United Kingdom. I'm not entirely sure how united it's going to remain and for how long, but I'm from a place called Bristol that recently found itself in league with Scotland and London in a referendum, and so maybe there's a breakaway republic. I don't know, but Bristol is a small city about the size of Tel Aviv, actually, but one thing I can say, regardless of what happens, it is in England. And so I'm going to pick on somebody English, William Shakespeare. Doesn't get much more English than that. And this is what he wrote. To be or not to be, that is the question. And there's a whole load of stuff there. And this is a fairly famous piece of a soliloquy. Fine. How would you write it if you were doing this as a software developer? Yeah, probably a lot more like this. This is from a book called Long Words Bother Me by Tom Burton. It's a lovely book on language. And he says, well, how would we do this? How would we do the great soliloquy, to be or not to be, if we were writing in business English or market speak? Continuing existence or cessation of existence, those are the scenarios. Is it more empowering mentally to work towards an accommodation of the downsizings and negative outcomes of adversarial circumstance? And so on. Now, I'm going to say, as a native English speaker, this makes no sense whatsoever. So if you're struggling, don't worry, okay? But this is the problem. What we do is we say, well, I'm going to be really clear. We're going to add more stuff. We're going to just be sure about stuff. Actually, this is, we'll just use that framework, bring in this, bring in that dependency. I need to be really clear about that. I could call one function here, but actually I'm going to really spell it out so that anybody reading this really understands. I'm going to use big words to really make sure they fully get the meaning of the code. Actually, software developers wouldn't write it like this. They'd write it like this. Because there's some really crazy patterns of indentation out there. So we actually see this in language. There is a tendency to try and add more. We need to make it more generic. We can't use simple language. Small words like to be or not to be, these are tiny single syllable. A child could do this. I'm a real software developer. Continuing existence or cessation of existence, okay? You see my credentials? I'm good. That's how good my software is. I don't want to write code that other people can understand. Oh, I'll say that I want to write code that other people can understand, but they're only the best people, okay? So we have this problem. So I'm going to pick another Shakespeare. This is the monstrosity in Love, Lady. The will is infinite and the execution confined. Your imagination and desire, you can create anything. That's the point of software. But there are limits. It turns out that when it goes from here down to here into that, there are constraints. There are constraints of time, there are constraints of memory. And the disappointing thing that many people have discovered is the speed of light is not configurable. That is your limit on the network. It turns out there is no config file to make it go faster. That is your ultimate limit. We thought it was fast, but the minute you hit the network, everything is slow. There's so much to say, so much to stream, so much to download. The desire is boundless, the act is a slave to limit. We will hit limits. So why don't we try and have a look at what those limits are? Now, one of the interesting things that is sort of a tangent. So I've written a bunch of stuff. I've been involved in various committees. I work for myself. I run workshops, do code reviews, do process reviews. And just for a bit of fun, I write short fiction. And it's very short fiction. Like really short fiction. It's called flash fiction. It's typically under 1,000 words, often under 500 words. And there is a word limit that when you submit a story, people will check it. If there is a competition for which it's a 500-word limit, 501 words gets disqualified. It's not about 500, it is 500. Yeah? Strict use of the less than or equals operator. And what is interesting about this is it's not 500 words of a story, it is a story in 500 words. Now, clearly, I'm not going to do Game of Thrones. That's not going to fit. But it turns out there are some stories, just like there's some music, that fits into a short format. We're not talking Game of Thrones here. We're talking YouTube videos, okay? We're talking that kind of range. And stories exist at that range as well. And one of the things I have learnt in flash fiction is you really learn to make your words count. You understand, do I really need that word really that I just used in the previous sentence? Really is a noise word. And it turns out that a lot of our code is noise code. If somebody said, I want you to go into your code base tomorrow and I want you to delete 10% of it and still have the same functionality. There's a kind of like a fear. Could you do it? Could you do it? And then I want you to do the same again next week and the day after and the day after and so on. And people kind of go, no, I can't do that. That's one of the things we do with flash fiction. It's really interesting. Okay, so you've got an 800-word story. I want you to make it 700 words. Now find the essence of the story, make it 600. It turns out you can do this with code. But sometimes we've picked up habits that we kind of think, oh, but I really need to log everything. You know, that's actually a test I use for people whenever I ask them, what are you logging? What's your philosophy of logging? Oh, we log everything. Oh, you have no idea what you're logging, do you? There's no such thing as log everything. When people say log everything, it means we have no idea what we're doing. But we don't want to say that because it sounds like we're scared, okay? You know, I just ask simple questions like, do you log the log action? Yeah. Oh, no, we don't log that. Well, what about this? Do you log the assignment of that value to that variable? Well, no. Well, in which case, I mean, I'm going to be a really pedantic programmer at this point and say, I have a very well-defined concept of the word everything. And you've just defined a subset of everything, so therefore it is not everything. What is that subset? And at this point, you get a conversation. One of my favorite authors, Neil Gaiman, he started, it wasn't quite flash, he was going to write a short story. A few thousand words into the short story that was only going to be 2,000 or 3,000 words, he realized this is going to be a long short story. A little bit further into that, he said, you know what, this is going to be kind of a novella. And he contacted his publisher. When he hit the 50,000 word mark, he said, okay, it's a short novel. So he missed by about an order of magnitude or so. So I do know of that particular, that book was Ocean at the End of the Lane. So there are cases. I also know of the opposite. Science fiction author based in Bristol, a guy called Gareth L. Powell, he set out to write a book and ended up with a short story of 5,000 words. So he was off by an order of magnitude the other way. So, you know, but I don't know of anybody who started to flash and ended up with a novel or a saga. That's not to say it hasn't happened, I just don't know about it. But we do know that that's happened with software systems. Okay? I meant to write a memory manager, but I ended up writing an operating system, said Linus Torvalds. You know, it's one of those accidents that happens. But that actually, it didn't accidentally happen. It was a process of growth, and that's something we need to consider. What I have learned, though, is the value of words and the value of throwing things out. And that thing you thought you always wanted and always needed, turns out that essential function, that essential class, that beautiful abstraction, some of them you can get rid of. This is a book that I co-authored a few years ago, Frank Bushman and Doug Schmidt. Pattern-Oriented Software Architecture Volume 5, or POSA 5 for short. This is all about pattern theory, design pattern theory. I would love to tell you, if you don't know about design patterns, this is the book to go and read. But it's not. It's the book after that you first learned design patterns. So you need to have read a few other books before that, which is why this is not a best-selling book. But I do like this book because it means whenever anybody asks me an obscure question about pattern theory, you can say, oh, it's in the book. That's actually why Frank and I wrote it, because people kept asking us questions. Where do we find out about this? In the book we have not yet written. Now it exists. But we made some general observations about software. We reflected on the nature of software. We reflected on the nature of architecture and a bunch of other stuff. And we also used some Star Trek and Hitchhiker's Guide to the Galaxy jokes peppered in through the pages. Oh, and Monty Python. When we talk about style, when I'm talking about flash fiction, when I'm talking about small pieces of code, sometimes people say, well, yeah, that's fine. You've got a small piece of code there. But we've got a big system. We have an architecture with a capital A in bold. It's really big. So this stuff you're talking about with these small little pieces of code, yeah, that's kind of interesting, but we're doing big stuff. The thing about software is fundamentally different to other constructed physical stuff. Because in software, your stylistic habits at the smallest level, there's a kind of an inflationary model. As your system grows, those stylistic habits become your architecture. In software, we do not change substance as we go down. Let me explain that. In building architecture, given that we use the architecture metaphor, in building architecture, you build large buildings out of things like bricks. You do not build large buildings out of small buildings. And you do not build large bricks out of small bricks. In other words, you change. It has a leveled concept. In software, you build large software systems out of smaller software systems. And you build smaller software systems out of smaller software systems. And boundaries get introduced. Sometimes there are network and organizational boundaries. Sometimes there are process boundaries. Sometimes there are class and other module boundaries. But the idea is you're building software out of software. And it's turtles all the way down. So what happens is that the small habits become your large scale. We can see this in something like the classic MapReduce algorithm. MapReduce is simply a functional programming idiom. And then if you do that functional programming idiom and you inflate it and you scatter it across a network, you get MapReduce as the architecture. The small idea is still there. I can still explain it in its original form, and I can still scale up the idea. But you cannot build a town the same way that you build a house. And yet we can build software this way. It is recursive. It's scale-free. So the small stuff matters, it turns out. And we also have a little bit of physics envy somewhere. Beautiful code. It's a lovely book, this, actually. It's a lovely book, and there's an example in this book that when I first encountered it in its original form, I thought was like a profound work. Its original form comes from this book, published in '99 by Brian Kernighan and Rob Pike. That's the sort of the demigod Brian Kernighan of Kernighan and Ritchie fame, and Rob Pike, one of the co-inventors of the Go language. Teapot, The Practice of Programming, it's a really nice little book. It's very understated. It's got simple ideas. So simple you think, this doesn't matter. That's why they matter. And it was a really good example as I was flicking through it, reading through it one day, and I came across this stripped down version of grep. It's a tiny, tiny thing, a stripped down version of grep. It's obviously not the full functionality. It's not the full regular expression pattern matcher. And it fits on a screen. It fitted over a page. And I remember just kind of glancing through it and going, where's the rest of the code? Rob Pike produced this in an afternoon. It's actually it's a ridiculously elegant piece of code. It's written in C, and what is nice about it is that it actually uses, it's very idiomatic to C. You could, if you were to write this in Java, it would be 2 or 3 times as long. It uses C for what it is. It says, okay, what can we do here? How does this language work, and what can nothing obscure, it's not doing anything kooky, it's just saying what is the natural idiom of this language that allows me to express these ideas. It uses a non-trivial example of mutual recursion, so we don't have to victimize people with factorial functions to teach them recursion anymore. We can actually use something that's vaguely useful. And it's really quite elegant. And you know, you look at it and go, there's a lot of stuff going on here. It actually uses the common subset of regular expressions. And this is small. Now, I'm not saying go out and throw away your regular greps, but the fact that this fits on a page, if I were to give this to an enterprise team, they'd be back in 6 months with something that didn't work. Okay? He took an afternoon, and it's really rather elegant. Now, we can obviously take this to an extreme. This is one of my favorite pieces of code by David Horn. It was written in 1983. A games programmer, Thaddeus Frogley, once blogged about it over 10 years ago. He said, this is the greatest program ever written, which is quite a claim. I mean, if you're going to say that, you better have something to back it up. This is Z80 assembler, and it is for the ZX81 home computer. It's a small world. I ended up talking to the cab driver yesterday about computers from the early 1980s, and he had a ZX81, which is kind of crazy. I come all the way to Israel to talk about a kind of obscure English home computer. Yeah, this had, how much memory did a ZX81 have? Anybody want to take a guess? 64K? No. 1K, good God, 64K. You must be rolling in money, and oh my God, what would I do with the other 63K? I have no idea. I mean, we've now reached the point that a few years ago, when my older boy, I mean, he's just been about, I don't know, 9 or 10, and he was reading a sort of a consumer electronics magazine, and he was going through, and I said, Do you understand what you're reading here? You know, some of those abbreviations like GHZ and you know, and GB and stuff like that. And I said, right, that's gigahertz. Hertz, this is what hertz means, and that's gigabytes. This is what a byte means. So there's gigabytes and megabytes. When I got down to kilobytes, he just looked at me and said, "What is the point of a kilobyte, Dad?" You know, just, why would you even name such a small thing? You know, why does it deserve a name? I was like, I haven't even got to byte yet. Yeah. 1 kilobyte, it's one of those things like, oh, that's all we had. That's all he had. This program fits into the ZX81 memory. It fits, actually, you don't get a full 1K because there's the runtime. You get 672 bytes. That's how long this program is. This is a chess program. This is 4.8 tweets long. Let me translate that into 21st century. 4.8 tweets. It can play a basic game of chess. It doesn't do castling or en passant. It does basic chess. It can recognize. It will play against you. I mean, it's not exactly, you know, deep blue. It will play against you. It'll recognize a win or a draw in 672 bytes. You can't even describe the game of chess in 4.8 tweets. Yet and somebody forgot to tell David Horn that this was not possible. When you forget to tell things like that to people, they go ahead and do it. Okay? And this really is, I mean, this is quite astonishing. You might say, well, we don't need to worry about that anymore. Well, actually we do, because it's not that this is a practical piece of code. It is the very possibility of this. It is the thought process that went into this. Whenever people say, oh, we've always got more memory, you know what we do? We use it up and say, well, can I have more, please? You give me 64K, I'll be wanting to know where 128 is. Yeah? We care about this stuff because we always need to optimize something at some level. Okay? There is always the desire. We fill it up and our imagination, it goes back to our infinite will. There's always a way to fill it up. So if you can come up with a trick to do this, then this is the stuff that people use in space probes. It's also the optimizations that allow people to cut milliseconds to microseconds. These are the things that matter. So it's not the specifics of the code, it's the mere possibility, and it's small. There's a sort of an elegance here, but perhaps not in the logic. Now, just as an aside, this record remained unbroken until early last year. This is called boot chess. It fits in the boot segment of a computer, 512 bytes. Outstanding, yeah? And if you encode it, it still fits. There's a beauty to this as well, okay? So this is kind of interesting, but I actually want to talk about something else when I'm talking about small. So first of all, I want to talk about it is possible whenever somebody says, oh, we don't have enough space, you do have enough space. Whenever somebody says, it'll be too slow, you can make it faster. But now I want to shift focus to the actual sort of code aspect here. Now, Oscar Wilde did observe that stuff like that, a work of art is the unique result of a unique temperament. You have to have a particular mindset for that. So perhaps I want to make something more accessible for you. Let's talk about the source. David Evans gave this wonderful talk at Agile Cambridge last year on testing. He's an Agile tester. And he just made this wonderful remark. Your customers do not buy your software by the line. Now, I can sense that there are a number of programmers out there who are disappointed by this because they're thinking, well, you know, that's the way I write. So therefore, the line of code, the lines that we preserve, are more of a liability than an asset. And it's worth kind of considering it from that point of view. Each line should count towards the functionality. Not so that it becomes cryptic like the examples I've just shown, but so that it is direct. It's a little more like the Shakespeare example than the chess example. Going back in time, again, this is my copy of the John Lyons book. John Lyons was a professor at the University of New South Wales. And in the 1970s, he wanted to run an operating systems course. And he wanted to use a realistic, real operating system, rather than a toy operating system. And at around that time was the time that AT&T, Bell Labs, for reasons of antitrust, had to basically get out of the operating systems market. You know, their Unix was seen to be in competition and against their kind of core business. So they released the source code. And he basically did an annotated version of it. Here is the Unix kernel and how it works. A complete explanation of everything. Before it was published as a book, the course notes are actually passed around by samizdat, as you can tell. People were photocopying. Now, for those of you who are too young to know what a photocopier is, it's like a social version of a scanner. Okay? You hang out at a library hoping to meet somebody interesting whilst copying. Yeah, modern scanners are a lonely business. Okay? It's great to have them in your home, but there's no sociability to them. Yeah? But the point I want to make here, this is Unix 6th edition. The whole of the source code, the whole of the kernel fits in under 10,000 lines of code. I think it's 9,500 lines of code. And about 5% of that is actually assembler, which at the time, this is astonishing to be able to write an operating system with that much portable code and that much non-portable code. I still know programmers who can't do that. As in, I'm writing for this platform, but you're using a language in which you could write something portable. I'm using Java. It should be portable, but somehow I've cleverly crafted it so it won't actually run on anything else. These guys were using C, and they managed to write 95% of the logic of one of the most efficient and influential operating systems in a portable fashion. So when somebody says that's not possible, you direct them here. Now, why am I showing you this? Because every now and then people will show me a class and they will say, oh yeah, this class, this code needs to be this big. I had a sort of an accidental contest with my co-author, Frank Bushman, a few years ago. I was talking about a class that I had seen that had 20,000 lines. That's 2 operating systems, okay? I can buy 2 operating systems worth of that. What was this class doing? It was receiving messages and then passing them on. Really? It takes 20,000 lines to do that? Oh no, we've got another system over there where we've got 50,000 lines that takes messages, changes the format, and passes them on. That 20,000 line class became a 1,500 line class. That's an order of magnitude. If you imagine that on a sort of personal level, if somebody came to you and said, I've got a 1,500 line class, if they told me that out of the blue, I would say, that's probably too long. It used to be 20,000. My God, that's amazing. How did you get it so small? 1,500 is beautiful, okay? The point there is that we've ended up with this stuff that we've forgotten. So you go through this book, and there's a kind of a nice, it feels like the 1970s when you look at the coding style. And you think, oh, that's not very good. And then you kind of pause for a moment and say, I've actually seen worse code recently. And it didn't do anywhere near as much. It didn't have the intelligence or the kind of the creativity. And this is an important point. The late Dennis Ritchie and Ken Thompson made the observation. They said, there have always been fairly severe size constraints on the Unix operating system and its software. Given the partially antagonistic desires for reasonable efficiency and expressive power, the size constraint has encouraged not only economy, but a certain elegance of design. It is not simply that these constraints exist and that's inconvenient. It's the very existence of the constraints that has created the software in its form and has given rise to some of its better properties. So this is a very counterintuitive thing, because people say, oh, if only we didn't have a time constraint, if only we didn't. Actually, you know what? That 128K, I'm going to cut it back down to 64K. That bandwidth, we're going to reduce it. Yeah? All of the constraints, reduce it. You're not allowed to use every dependency on the web. Reduce it. Okay? And suddenly you discover there's a simpler way. You discover that your dependency set, thank you very much, has reduced. Stravinsky observed, the more constraints one imposes, the more one frees oneself. This is one of these counterfactuals, this counterintuitive. The arbitrariness of the constraint serves only to obtain precision of execution. So when I joke about writing stories, there's actually a flash fiction form called a drabble, 100 words. Exactly. Not 99, not 98, and certainly not 101. 100 exactly. Some of my favorite stories that I've written have been exactly 100 words. And when somebody gives you a 500-word limit, don't just do 450, do 500. Exactly. That constraint feels really arbitrary until you use it, and suddenly you get a new idea. So sometimes when we work within a language that has a constraint, sometimes having a language that allows you to do anything is actually a disadvantage. Sometimes having a constraint like, oh, you're not going to work with side effects. Okay. How do I do that? Well, guess what? You can. You just need to be a bit more creative. It's the creativity. That will give you a more elegant and sharper solution. So it also gives us a philosophy. Koenig and Plauger, you'll see that I'm basically picking books from the last century, mostly, because it turns out none of these ideas are new. Beautiful Code was this century, and so was the one I wrote. This philosophy has been around for a ridiculously long time. Our understanding of how to work with large systems is based on a very simple concept of bandwidth. The bandwidth limitation, am I talking about network bandwidth? No. The bandwidth limitation is this. It turns out that while something like building architecture has a natural scale, the natural scale of building architecture is the human being. If you look at any building, it doesn't matter if it's a skyscraper or a garden shed, it's based on the scale of a human being. If you look at a building that is supposed to be impressive, the reason it's impressive is because you are a human being. Okay? I went to Cologne a few years ago, and the cathedral in Cologne, I've always been told, is very impressive. You come out of the main station and go, wow, that's a really big piece of Gothic architecture. And it's big, but if you are a giant 400 meters tall, it's not very impressive. Okay? The whole point is that it's designed for the human scale. It's designed to impress the humans at that scale. That's what it's for. So all architecture is grounded in a natural physical limit. Software is not. What is the natural scale of software? Well, it doesn't really have a hard limit, but I'll tell you what the natural limit of effective and sustainable software is. It's software you can fit in your head. Not the whole of it, but you can break it down into pieces that you can load into your head. If I can understand a function, a class, or whatever easily, then I will work quickly and confident with it. It may be connected to a larger system, but if it is loosely coupled, I can reason about these things at distance. So normally people try and motivate coupling through very abstract computer science. Forget it. You can motivate it through psychology. Okay? The human brain gives us a natural limit. We are not very good at holding lots and lots of stuff at once and not dropping something. It's not that you can't work on something that is large and complex and highly interconnected and very legacy. It's the fact that you will slow down and you are more likely to make errors. But when you move quickly, it is because things are small and you can say, oh, I understand that. I don't need to go any further with it. I can change that. It's easy to reason about. So that's where we get to this limit. So this is why this is here. It's because of us. All these limits are not natural limits in the universal sense, and they are not computer science limits, so they are not mathematical. They are actually us. And then we get the surprise of simplicity. Simplicity contributes to size immensely. This is an email that quotes Ward Cunningham. Ward invented the wiki. So this is from 1996. I used to use the original c2.com wiki in the late 90s. And so John O'Dell from Byte Magazine, he gets this email from Ward. So what do you think of Wiki? I put it up a year and a half ago when HTML authoring tools were in short supply. I think it has held up pretty well, though I suppose its days are numbered. Ha, you got that one wrong. Okay, Wiki has taken over the world. In other words, it's the whole concept. It's so ridiculously simple. And if you look at the original Wiki source code, this is the top and tail of the original generated file. It's about 150 lines of Perl. Perl being my least favorite language, possibly. There are some other ones. Executable line noise, as a friend of mine described it. But he's used it really well. This was the era of CGI. What he's done is he's used it idiomatically in the context for which it was kind of intended and lived naturally. And he created something that was so trivial and silly that nobody would ever use it. Well, it had such a trivial form for editing web pages. A very trivial kind of markdown style approach. In fact, it makes markdown look complex. Okay? It's just one of those, come on, you know, that's never going to catch on. If you're given this task, we want web editing, so people can just go in there and interact with pages and comfortably add content easily. If you gave that to a typical software team, they say, right, see you in 18 months. We've got this amazing thing. And it's just like, yeah, well, you know, the market's beaten you to it because they did stuff like this. They chose something that was so simple that when you look at it, you can see how to extend it. You can build your own. You can take the idea. And Ward evolved this. The original version pretty much had no security. Okay? And he evolved it. And we evolve it with version control systems, embedding of content, and so on, with richer content. And this is a growth model. So the idea is that most of the ideas people dismiss as being, oh, that's too simple, that's too trivial, turns out are the ones that people will actually pick up and use. HTML was originally criticized as being too naive and simplistic as an HTML approach, as a hypertext approach. Hypertext research in the 1980s basically said, this is how to do hypertext correctly. Tim Berners-Lee comes along with this thing that has broken links and stuff like that, and uses a simple subset of a markup language. This is stupid. This will never catch on, said the real hypertext people. I don't know where they are anymore. They're gone. They left the building. It turns out that the simple idea is an idea you can fit in your head, and you can expand and grow from there. We like to complicate things. Sometimes we use meetings to complicate them. Sometimes we use wikis to complicate them. The idea is we take a small idea and we won't leave it alone. Okay? It's like, your mother always said, you've got a scratch, leave it alone. Oh, no, it's a marketable scratch. Yeah, I'll turn it into something really big. And yeah. There's this other aspect of constraints. So, my colleague Chris Oldwood, lovely tweet, isn't a notebook screen a bit small? He said, no, if the code doesn't fit on it, it's too complicated. And there's an interesting constraint. All too often I encounter people saying, well, no, it's okay, I've got this kind of like, iMac size screen. I can have, I've got, those long lines. It's okay, they've got their own weather system, they're so long. And I'm not joking, I did encounter, 2 years ago, I did a code review in a company, and we were just looking through the code, and these lines kept disappearing off. It kind of looked like some kind of sort of erratic heart monitor, bit, boom. And it would go off the screen. And this was kind of like an HD screen. It's like, well, how far does that go? So we put on our hiking boots and we set out. And around column 360, we found the end of the line. They said, do we need a second screen? No, you need a line break. Maybe 10 line breaks, The point there is that we've ended up with some really crazy stuff. And some of it comes from some very curious habits in our code. Hemingway observed, eschew the monumental. Shun the epic. Forget this stuff. All the guys who can paint great big pictures can paint great small ones. We are too impressed and too easily impressed by concepts of size. Sometimes occasionally you look at a piece of code and you're looking at it going, well, there's not much there. Well, that developer can't have worked very hard until you look closely. It's just like, wow, that's really interesting. It just does exactly the right thing, and you don't need more. Where are all the flags? Where are all my switch statements? Oh no, we don't need those. This is just the right thing. To reflect that, Schumacher said, today we suffer from an almost universal idolatry of giantism. This is the 1970s. We really have it now. It is therefore necessary to insist on the virtues of smallness. But importantly, he's not saying everything should be small, where this applies. I don't think we look enough for where it could apply. We assume that everything is just going to grow without boundary. And part of this is that we have an ingrained idea that as things become successful and more popular, and therefore, we need to grow them, we assume certain things. We assume a model of the economies of scale. Now, the economies of scale are kind of hardwired into us from a very early age. Okay? The idea that, if I got one person doing something, then maybe if I get 5 people doing that, we'll save time. Okay? If I buy one thing, my youngest son had to do a sort of a school exercise with a friend where they were selling things, and they did the standard thing. Okay, well, we'll sell you this for 2p, and so this is 2 pence, this is 2 pence, but you can get 3 for 5 pence, or in fact maybe 4 for 5 pence. Yeah, that's a better deal. So in other words, they've got the economies of scale. If you buy more, we're going to make it cheaper for you. This is the way that so many industries are run, and it's ingrained in us. But software's not like that. There's actually quite a lot of things that are not like that, but software is one of the things that is not like that. It's informational. And I'm going to say, interestingly enough, going back to the fiction, I wrote a 500-word story a couple of years back, and it was actually harder than writing a 2,000-word story, because you really had to find the heart of it, the essence. What is it really about? 2,000 words, yeah, I can do that. Oh, you're going to give me a whole Game of Thrones saga? Yeah, I can just keep on typing. I have no constraints. And you see that in some writers. You see it in some code. Some code? Lots of code. You see it in lots of code. There's no economy of scale. It doesn't get necessarily that easier, in truth. There's not less effort when we actually grow this thing the way we expect it. Software development, or development, has diseconomies of scale. This is an observation made by Alan Kelly. And he uses an example based on milk. You can do the same thing with glasses of wine. If 4 small cartons of milk have the same volume as 1 large carton of milk, the one thing you can be sure of is these will not be a quarter of the price. They will be a third of the price or something like that. Okay? You cannot, if you're thinking of buying some wine, it's not simply a case of have some wine and, oh, that's 5 glasses, that's a bottle. Well, 5 glasses is the same as a bottle. No, it isn't. A bottle is cheaper, even though it has the same volume. It's ingrained into us. Software is the opposite. Now, why is this the case? It's the expectation. As he says, we think with or through ideas. And what we think of as thinking is generally the application of pre-existing ideas to a given situation or set of facts, Gesundheit. And this idea of thinking through an existing situation, it's kind of a bit like patterns. I'm talking about architecture, I've talked about buildings, so I'm going to refer to one of the original patterns books. Patterns did not come from software, they came from building architecture. The work of Christopher Alexander, Timeless Way of Building. He contributed to a rather unusual cover of a book, or a rather unusual book with an unusual cover, Design After Modernism. He wrote this piece, "A city is not a tree," which is kind of an obvious statement because a tree is a tree and clearly a city is made of buildings and roads. But what he was actually referring to was the concept of hierarchical nested structures. He's basically saying, look, there is a structure here that sometimes we overcomplicate things. If we try and organize a large-scale thing using overly simple ideas. So now I want to go to the other side of simplicity and say there should be a reflection of actually the way that humans think and interact in the way that you work with your software. When you push against it, it makes software larger. Now this is very counterintuitive, but I'll explain it. So first of all, I'm going to start off with probably something that's become very, very popular recently. So, quick show of hands, who's heard of Conway's law? Yeah, okay, we're on the upslope, because when I did this 5 years ago, people were looking at you blankly. So everybody's talking about Conway's law. It goes in cycles. We included it in the Poser books before it was popular. I first heard about it in the 1990s. This is actually a diagram from the original paper. Melvin Conway published this in 1968. This is where it originates. How do committees invent? The basic thesis is that organizations which design systems are constrained to produce designs which are copies of the communication structures of these organizations. And this has been repeatedly demonstrated. We've got much better code analytics than he had in 1968. In fact, I don't even think he'd know what that meant. And I had the privilege of meeting Melvin Conway, still alive and still very fresh mind, as I met him last year. What we're seeing here is that there is simplicity of an idea, but software is not created in a vacuum. This is one of the really interesting differences between software developers and writers. Sometimes you really understand the differences between them. Although we both write, we are both composing something. It's informational. A book is an informational concept. Software is a complete work of fiction. I mean, it's totally made up. I mean, really, that stuff doesn't exist. And your abstractions, they don't make any sense whatsoever. There's nothing like that in the real world. It's executable fiction. That's a really useful way of thinking about software. It's a story, you made it up, and it should have good, compelling characters and a strong plot, okay? And it should make sense. These things we have in common, but we also have some major differences. Sometimes people accuse software developers of being very insular and introverted and antisocial. This is, of course, complete nonsense. Who invented email? Software developers. Yeah, granted, it's not exactly standing face-to-face at a party, but it is a communication. Okay? How is most software developed? Most software is not developed by individuals. It is developed by teams, organizations. How are most stories written? They are written by individuals. Writers make all software developers look like party animals. If you've never met a writer, they are really introverted. Yeah? The whole idea of social anything with writers is quite difficult. So there is something here that we have to respect, is the fact that software becomes an artifact of a group intelligence. And so it's not the only thing that's informing it is natural cohesion and individual structures. It is this idea of interaction and how people will work. If you push against that and you try and impose a hierarchy where there isn't one, the software will push back. We've seen from this fact that it has important implications for the management of system design. A design effort should be organized according to the need for communication. In making this observation, it tells us that structure of communication is fundamental. Where do we see that, and how does this reflect in quality? A very interesting paper, it's nearly 10 years old, from the MIT Sloan Management Review. You can download, you can read one paper from this site for free. I strongly recommend this one, Avoiding the Alignment Trap in IT. And they observe that one of the biggest problems, IT's effort to satisfy the various and sometimes conflicting business constituencies created a Byzantine overlapping systems that might satisfy individual units for a while, but did not advance the company's business as a whole. They are observing existing organizations and the problems of quality and technical debt that they have. And this is the interesting thing. They did a survey of over 500 companies, around 500 companies, and it's a quadrant diagram, so this is management friendly. Okay, you divide the universe into 4, and there's normally either a very bad quadrant or a very good quadrant. This one has both. Along the horizontal axis, how good are you at software development? Not you as an individual, but collectively as a team. One of the things that we've discovered is that group intelligence is not always related to individual intelligence. In fact, sometimes it's inversely correlated. We recently demonstrated this in a referendum across millions of people. So it turns out, the group is much dumber than the individual. But you can have a group of individually motivated people who don't work well together or are not given incentive to work together. So this is an important idea. We're not saying that somebody who's not, a team that is not effective does not necessarily have ineffective individuals. They can be individually intelligent, but they're not effective as a team. In England, we also do this with our football team. What about this axis? This is the business speak axis. This is alignment with the business. The degree to which the IT organization has the same agenda, the same priorities, and works with and in the business. And normally we assume more alignment is better. And a lot of organizations move in this direction. But let's look at the numbers. First of all, the no surprise quadrant. 3/4 of the companies are not particularly effective, and they're not particularly aligned with respect to their IT. But it turns out that's not as bad as you think. We're not really losing money, and we're not really making money. So it's not actually a complete disaster. We're probably in equilibrium with the rest of the organization that has exactly the same problems. Up in the top right-hand corner is where everybody wants to be, but if you look at the numbers, there's only 1/10 of the people who are in this quadrant. IT-enabled growth. We are highly effective and highly aligned. Wow. Growth of 35% and the costs are going down. Everybody wants to be up there. The problem is that if you're in this quadrant, most people will push you into this quadrant. Become more aligned, don't worry about becoming more effective. Don't worry about the technical debt, don't worry about software craftsmanship, don't worry about the code quality. Don't worry about that dead code. And guess what? It becomes more expensive and you become negative growth, which is one of those polite ways of saying shrinkage. It turns out that if you go the other way and you don't worry about alignment, but you just get really, really good at what you're doing, it turns out that is surprisingly effective. It's almost counterintuitive. Except when you realize, as this guy observes, aligning a poorly performing IT organization to the right business objectives still won't get those objectives accomplished. It does not make a difference. In fact, you frustrate them. You have people who are failing all the time and are frustrated by that. If you imagine the code produced by these teams, I want you to imagine we've got a team up here and we've got a team down here. We tasked them to develop a system. These guys just about deliver it. They got it, it's got the right functionality. It's a little bit buggy and you really don't want to see the code. It's filled with noise and accidental complexity and all kinds of stuff. Down here, we weren't really listening to the business, but we've got you a system. It's really good. Yeah, it's really fast. It doesn't do quite the right thing. Now, normally people joke about that as if it's a really bad thing, but I want you to imagine version 2. Which code base do you want to work on? Oh, well, ours doesn't do quite the right thing, but it's got really low technical debt and we've got some tests for it, so it should be easy to make it do the right thing and then add new features. This piece of code is like a Jenga game. Just don't move anything because it'll all fall down. This is the point. The getting good allows you to throw out the stuff. Now, when we talk about this kind of thing, we've got to talk about various things of scale. So if there's anybody who works for Facebook, I really apologize. Actually, no, I don't. I read this last year, Facebook's code quality problem. Really insightful blog. The Facebook iOS app has over 18,000 Objective-C classes. 18,000. What the hell are they doing? Dear God. I mean, I was joking about operating systems earlier on. No, I'm not. This is bigger than most operating systems ever need to be. And it's sitting on a phone. And really, I'm sorry, I mean, Facebook's very, it's quite cool. There's some really good ideas in there. There's some really great thinking. But really, that is a fundamental problem. Over 400 people contributing to it in a week. They've got their hands all over the place. One of their big discoveries is that when everybody goes home at the weekend, they get fewer quality problems. So this is insane. How did it get this way? There's something wrong here. So let's talk about economies of scale. Let's go back to these numbers. 400 people to develop a mobile app to say, look at my breakfast. Okay, I am trivializing it a little bit, but at the same time, there is an element of truth there. So let's start off with something really simple. Imagine we're going to develop some app. This is the time taken for one person to do everything. To develop it, to deal with requirements, to do the testing, all these bits and pieces, and deal with deployment and so on. One person's job. At this point, somebody kicks in and says, yeah, I've read Adam Smith, economies of scale, division of labor. We're going to get N people working on this. And we're going to cut the time by N. Okay, sounds good. But that's an ideal thing. If you ever studied electronics at school versus electronics at university, one of the things they gave you at school was, in all the problems, they used to use superconducting wire. They never said it was this, but they used to say, imagine the wires have no resistance in your circuit. Superconducting wires. I can't afford superconducting wires at home, but apparently when I was 15, yeah, we had them, at least on paper. It's an idealization. It's an oversimplification. Because we need to take into account how much can you do in parallel. Just because you've got lots of people doesn't mean that they can do everything in parallel. How does the task break down? Are people waiting on other people? How have you organized your workflow? Am I sitting here waiting? If I'm a tester, am I waiting until somebody finishes software? Oh yeah, we'll be with you in 3 months because we're going to give it to you in one big batch. Am I waiting for somebody to give me the marketing message? Am I treading on somebody else's toes? How much am I waiting for? The portion in parallel. So it turns out that, unless P is 1, you're always going to be a little bit slower than you were hoping for. It turns out we already knew this. This is Amdahl's law. We normally talk about it in terms of processes, but hey, people. So there's this, but we're not done yet. There's this term. This is to do with connections and people's communication. And there is a cost to communication overhead. This communication overhead gets reflected in the code. If you get 100 people to work on a piece of code, they will produce a 100-person-sized piece of code. If you get 10 people to do the same thing, it'll be a 10-person piece of code. Okay? It will end up looking like that because people will justify their work by elaborating, but they will also adopt defensive postures, distance from other people's code. I don't trust that code. I saw one system where if you'd asked me, what does this code base do? I would have said, it checks for null. Because that's what most of the code did. Every single argument, well, we don't trust where that came from, so check it for null. We don't trust what we got back from that method, so check it for null. The CPU spent most of its life checking for null, and in between, it would occasionally do a mortgage application. Okay, but that was incidental. The whole code base was a reflection of the people and how they worked on it. It was unnecessarily large. So this obviously gives us a nice curve. Number of people, amount of time. Intuitively, when you've got nobody working on it, it will take infinite time. But it'll have no bugs, so, And then you start increasing. This is good. But then you've reached the optimal point, beyond which when you start adding people, you are not getting any benefit. You are not harnessing the intelligence of the group. You're actually now causing the group to break down and things slow down. Most consultancy companies work over here. We've got lots of people doing actually what 1 or 2 people could probably do quite effectively. And because people get used to it over here, people will say, well, I hear what you're saying, Kevlin, but our system's really big. We're very special. Our system needs to be millions of lines of code like this because we are special. It needs those tens of thousands of classes because we are very special. Look how many hundreds of people we've got working on it. That's why we need this many lines of code, or they'll do it the other way round. We've got that many lines of code, so therefore we need this many people. And You steadily climb up the curve. The problem, occasionally I get asked by people, how do you know where you are on the curve? You want the bad news? The bad news is this curve is an idealization. It's a little bit lumpy. So sometimes you will think that you're going uphill and say, let's turn the other way, but actually you were in the right place. Sometimes you think you're going downhill. You must, adding more people. We must be over here. Actually, you're just in a local dip. You're about to go up again. This curve is a demonstration of the fundamental problem. This is the diseconomy of scale in action. This is where a lot of software companies operate. And this creates the quality problems, the urgency, the inability to tackle technical debt. And none of this is new. Fred Brooks said, what are the difficulties in software? Following Aristotle, I divide them into essence, essential complexity, that's the kind of the nature of the problem, and accidents, the difficulties that attend its production, that are not inherent. In other words, how you have chosen to work with your system. The technical complexity, the technical debt, the architecture, the complexity of the language, the libraries, the quality issues in the code. In other words, it's nothing to do with the original domain or the original application. It's all to do with how we chose to build it. As he says, how much of what software engineers now do is still devoted to the accidental as opposed to the essential. He wrote this at the beginning of the 90s. The question's still there. I think we spend too much time dealing not with let's build the application, but let's defend ourselves against each other and the application's complexity. So where else does the size come from? Cargo cult programming. Size comes from many different places. It doesn't just come from all these economic considerations or these accidents of history and these misunderstandings. Cargo cult programming is a style of computer programming characterized by the ritual inclusion of code or program structures that serve no real purpose. This takes us back to where we started. Cargo cult programming can also refer to the results of applying a design pattern or coding style blindly without understanding the reasons behind it. And we end up with code like this. I talked about the size of names on screens. I don't know if you saw this beginning of last year. Wonderful comic, The World Seen by an Object-Oriented Programmer. Visitor monitor interface, living space decorator, entertainment provider Singleton, multi-bus supporter. It's all here. This is how we name things. It's got insane. It's just like, why can't you just name it after what it is? And some people seem afraid to do that. I can't name it like that. People won't know what a door is. People won't know what a sofa is. I need to use these longer words. We've ended up, at the beginning of the 90s, I used to try and encourage people to use longer names. I now find myself, over 20 years later, trying to encourage people to use shorter names. We've ended up with these kind of like bolt-together names. I need my screen because the class name is 80 characters long. It's got to the point where you can find websites like this, class namer. Absolutely brilliant. You can just randomly refresh the screen. It'll give you a random class name. Yes, you got a choice. And this one is brilliant as well. You can do the whole code base as a method namer as well. Yeah, you could just sit there refreshing the screen, copy, paste into your code base. Yeah, that and a little bit of IntelliSense, and you never need to work another day in your life. Anybody seen the FizzBuzz Enterprise Edition? FizzBuzz is a drinking game. You count. By the way, it does need to be a drinking game. We tried this as a family on holiday recently. We were in a restaurant waiting for the food. The food was taking a long time, as was the wine. The wine had not yet arrived. So there's me, there's my wife, 10-year-old and 14-year-old. 10-year-old's really good with maths, so there's no problems in the room. We're sitting there, what should we do? Play a game. Okay, what about FizzBuzz? It's really boring sober because everybody gets it right. It's a counting game. 1, 2, fizz. Anything divisible by 3 is fizz. 4, buzz. Anything divisible by 5 is buzz. Fizz, 7, 8, and so on. When you get to divisible by 3 and 5, it's FizzBuzz. 13, 14, FizzBuzz. If you get it wrong, you have a drink. That's why it's a fun game, because once you start getting it wrong, you continue getting it wrong. And it's been used as an interview question. This is FizzBuzz Enterprise Edition. Enterprise software marks a special high-grade class of software that makes careful use of relevant software architecture design principles to build particularly customizable and extensible solutions to real problems. This project is an example of how the popular FizzBuzz game might be built were it subject to the high-quality standards of enterprise software. I do need to say this is a joke. This is a humorous site. Somebody did once ask me, is it for real? If you choose the right language, you can do it in a tweet and still have space for a comment. Okay? This is the interfaces. Okay, this is just one part, the interfaces to the factories. This is not the implementation. This is not the rest of the code. FizzBuzz output strategy factory. You know, they just went to classneighbor.com and just, yep, refresh. String return a factory. I love that one. This is accidental complexity in action. We have taken a simple idea, and I think I've probably got maybe 20 people working on this. It's going to be the best FizzBuzz ever. No, there's nothing to do with me, but you can imagine somebody doing that. So we've got the wrong size. Anderson's law, Poole Anderson. I've yet to see any problem, however complicated, which when you looked at it in the right way, did not become still more complicated. And we are very good at that, very good. Okay, so all code is technical debt. I think this is a really good observation from Paul McMahon. Some code just has a higher interest rate. So if you start out with a position that any code that I have is automatically some kind of problem, my goal is now to figure out which is the real problem. And the challenge is, sometimes we look at the code and we say, well, oh, don't worry about that code, it's dead code. We don't need it. Oh, so we're going to delete it. Oh no, it's okay, you just leave it there. How much does dead code cost? This is not a photograph I've taken, it's New York Stock Exchange. This is the story of Knight Capital Group, who suffered a slight loss in 2012 on the 1st of August. There's a really good write-up of this from a DevOps perspective by Doug Seven. Knight Capital Group realized a $460 million loss in 45 minutes. That's $10 million a minute. Outstanding. Actually, they managed a far greater loss. This is the loss, basically a software error led to a major loss. And there's a kind of an agreement that any inappropriate transactions that result from a software error are rolled back when we realize there's a software error. This $500 million is what was left after they reclaimed everything else. They lost billions during the day. $460 million is what was left over after they reclaimed everything they could. And he highlights this point. The update to the SMARS system was intended to replace old, unused code. So this is the update that occurred between the 31st of July and the 1st of August. It didn't go quite according to plan, but they're going to replace old, unused code referred to as PowerPeg, functionality that Knight hadn't used in 8 years. This is dead code. Now here's the interesting thing, and I think he gets this one slightly wrong, but it tells us why these things are interesting. Why code that had been dead for 8 years was still present in the code base is a mystery, but that's not the point. When things like this happen, and there are lots of incidents that happen like this, but this is very public, this one, they don't happen because of one thing or another. They happen because of one thing and another. It's not the fact that it was incorrectly updated. If that code hadn't been there and the system was incorrectly updated, then there wouldn't have been a problem. Or rather, they wouldn't have been trading, but they wouldn't have been losing. Had this code been dead, as it had been for 8 years, and there wasn't an incorrect update of the code, then everything continues as normal. It's when the two happen together, when there is a perfect storm. So what happened is that this code that hadn't been used, basically they did what many people do in such systems. They kind of reused, I can't remember the detail, they reused a flag or a status for something else. I've done that, I'm guilty. How do we extend this protocol? Yeah, let's not re-extend the protocol. Look, there's an unused byte. Right, let's use it. Oh, it used to be used for something else. Yeah, but nobody relies on it anymore. Let's change the meaning. And then we don't have to change the protocol layout. It's that kind of thing. And then what you discover is you have zombie code. It's not dead. It's come back to life with a vengeance. First 45 minutes, the market was open. PowerPeg received and processed 212 parent orders. As a result, SMARS sent millions of child orders into the market, resulting in 4 million transactions against 154 stocks for nearly 400 million shares. Algorithmic trading, doing the wrong thing at speed. That's what it's all about, okay? That's what optimization is about. This is the cost of dead code. The cost of dead code is not that you can guarantee it will happen like this, but it might happen. And this is the point, that it has an actual consequence. Very little code is dead. There are many examples of this stuff lying around. What does this mean, going back to the brain? What it means is that somebody has got to spend time going through that code to understand it. Oh, you're new on the team. There's the code base. Yeah, I wouldn't spend your time looking at that. I've just spent 2 weeks looking at it. Yeah, nobody uses that anymore. Oh, I've just been busy refactoring, and I've really kind of spent a bit of time refactoring here, and oh, yeah, that's actually dead. But you might have brought it back to life. This is the cost of size. We are no longer able to manage the thing that we are working on. Susan Sontag observed Our task is not to find the maximum amount of content in a work of art. Our task is to cut back content so that we can see the thing at all. If you look at a lot of companies, they cover the whole range of very, very large, noisy software that's become a problem, versus people who are trying new and experimental things and are able to throw out that version of the system. They're not just doing A/B testing, they're actually able to do proper renovations of their architecture. It's not just a front end, because they've broken it down to the level at which it is simple. They found the simple ideas, and what they're trying to do is reveal those. Oh, the system's become too large. Well, just keep adding. That's one fork on the road. There is another fork on the road. The system's become too large. Okay, let's figure out how we can cut it back, because we still want to be in the same game in 5 years' time without using hundreds of extra people. So this kind of perception I observed a few years ago is we keep talking about incremental development. We don't talk enough about decremental development. Making things smaller, throwing stuff away that we do not need so we can actually make the thing larger in a meaningful way rather than an arbitrary way. So leaving the last word with Ernst Schumacher, there is wisdom in smallness, if only on account of the smallness and patchiness of human knowledge, which relies on experiment far more than on understanding. This acknowledges that we cannot know in advance everything that we need to know, that we must experiment. But if you're going to start building stuff, you need to be prepared to throw stuff away. And we are very reluctant, even though it's abstract, to throw bits of software away. We will hold on to the code, and we will hold on to the accidental practices that led to it, and sometimes the thinking behind it. Okay, so basically, how do we reduce code? Because I made the observation about reducing by 10%. Again, I was throwing out an arbitrary constraint, but it's a good intellectual challenge nonetheless. But if we reduce it by 10%, do we just turn it into line noise? That is a genuine fear. So how do I leave it comprehensible? That's why I emphasize the literature aspect, partly because I like it, but also because it's a very good example that sometimes adding to something does not make it more meaningful. So how do we do this? Well, we're going to take advantage of one of the things that we do really well, which is other people. Other people. We often talk about things like self-documenting code. Yeah, that phrase pops up every now and then. Oh, I don't do comments because it's self-documenting. Okay, let's be very clear. The person who makes the judgment as to whether or not your code is self-documenting is not the self that wrote it. It is another self. If your colleague says, I have no idea what you're doing, then it's probably not self-documenting. I mean, you could say, you're just too stupid to understand, you know? But actually, what you've got is feedback. You've got feedback there that actually, we've turned this into line noise, it's too cryptic. So the goal is not simply to reduce it to, you know, the Z80 assembler. The goal is, can I extract, what's the essence of this? And sometimes the people who are too close to it cannot see that. They have a particular knowledge, but perhaps they don't have the extra insight or the awkward question. You know, the fact is that your colleague may have a different perspective, either because they had a similar approach but have now moved away, or because they genuinely have no idea what it's doing. And by using their ignorance constructively, and this is an interesting idea, but I think it's quite a powerful one, constructive ignorance. The very fact that you're dealing with somebody else who is clearly intelligent, and yes, software developers are intelligent even when they do stupid things. Yeah, we have some of the smartest dumb people of any industry. To be a software developer, you've got to be way up here. You know, you pick other industries, their dumb people are way more stupid than our dumb people. We have the smartest dumb people, okay? There's an entry level to software development. So the people you are dealing with, even if they don't see eye to eye with you, they will be smart, but they don't see eye to eye with you. They come from a different perspective. So they will ask a question, and that question can reveal something to you or to them. And it's just that's one of the ways you make it smaller. You kind of get another pair of eyes. And somebody will say, oh, what you're trying to do is this. Yes, that's what I'm trying to do. Oh, okay, well, what's this doing? Well, now you ask. I'm not quite sure what that abstract. It's because I thought I might need, you know, sentences that start like that. And it's like, well, now we know. You wrote that 6 months ago. Did you need it? You wrote it 2 years ago. Did you need it? Yeah, you know what? This is simple. I could just pass a lambda in. Oh, yeah, of course. I don't need mega construct fizzbuzz thing. I just need a lambda and that's it, and we're done. And sometimes you don't see that because you're so used to it. So another perspective, sometimes you can provide that, but sometimes another person, that will help you keep it inside. And eventually you'll reach a limit and say, no, at this point it becomes line noise if I reduce it any further. We're just, you know, the names have now become one letter long, and no, that's stupid. That's not, there's a Goldilocks principle, okay? Too long, too short, just right. That's where you're aiming for. So you will know when you hit this one, but sometimes we sleepwalk into the longer thing. Right, okay, so there's two things here. Sometimes we add things because the only way we know how, and that's actually an interesting challenge. Perhaps we're locked in a particular business model. And it turns out that sometimes taking away features or just repackaging them and minimizing them, that's one of the interesting transitions that we've seen, is a lot of people who interact with social media sites, they do so via mobile and they do so on the web. And what is interesting is that typically the mobile app is less featured than the web apps. It has fewer features, yet more people use it. That's interesting. So maybe it isn't worse. Maybe the shift in environment has actually caused people to find the essential core of what they need. Yeah? So one thing is to challenge the perspective. This is the way we know how we add stuff. So sometimes there's a kind of a pushback. Is that really how we should do it? But beware there, I'm not going to say it's without pitfalls. Somebody I know worked for a company that went out of business. And they made the terrible mistake of using an old business model but with new techniques. And their approach was, we will charge people for upgrades and new releases. And they built the product and it did exactly what people needed, and it was bug-free. You know, test-driven development, everything, it was just right. Nobody ever wanted an update. Oh no, thanks, it's just what we need. Oh no, there's no bug that's annoying us. No, we don't need the next release. We don't need to pay for it. The company went out of business because their code was too good. Right, now the problem here is that's actually quite a great story, except for the fact what they were relying on was an old business model but with a new approach. So you need to kind of move into that space very carefully. The other aspect is, even when we are growing for natural reasons, for example, actually acquiring new functionality because people are genuinely asking for it and that would make a difference to how they work, I'm not going to say the software shouldn't get bigger. I should say you should be actively assuming it's going to get bigger. How do you make something bigger successfully? By cutting out the stuff that you don't want. In other words, gardening. Okay, the gardening metaphor has been used a number of times, and I remember feeling really proud of using it when I observed my wife doing exactly this with the garden of an old house that we moved into. To make the garden beautiful, she would cut back stuff and experiment. Let's try that plant over there. That one didn't work. That one did. Let's move this over here. Or that's a beautiful plant, but it won't work in our garden, so it's not relevant. So in other words, that's a beautiful feature, but maybe it's not for our application. And she would experiment, and actively over a couple of years, the garden grew and became something completely different. I've got photographs to show the original form. But a technique the gardeners use is they cut back. And we need to learn that in software. It's the cutting back. Sometimes people use the gardening metaphor to just say, oh, it's organic and fluffy. I don't buy that. I think it's a very intentional act of experimentation, and it's a very empirical act, but you do so by finding out what works, get rid of the stuff so that new stuff can grow. And I think that's not the bit we're not good at. So the systems will grow, but the problem is, that's why I put this slide up, is I think sometimes what we do is we leave all the dead stuff, the half ideas, or the first idea I had for how to do this becomes the architecture, and it grows. And now we want to graft onto that, and it doesn't fit very well, even though we can think in our minds of a better way, and we just wish we had a time machine to go back and make that change. So I'm going to say actively engage in the idea of, gardening. So the system will get bigger, but it doesn't have to be as crazily big or as complicated as it might otherwise be. So I think that's the intentional approach. That's what I would offer. So there's two answers there. One is sometimes it's the business or the organization or the expectation that moves us in a direction, but the other is let it grow, but do so by cutting back. Okay, so the challenge here is that sometimes we may find the elegant heart of what we're trying to build, but then we add something and it loses that. And then we add something else and it loses that, and we don't have the time to go back. So one aspect is, the bad news is it's uphill. Everything that you want to do that is uphill. What I'm trying to say is that going uphill is actually worth it. Now, one of the things I do is I run, and I will say that running uphill is much better for you than running downhill, just as a general observation. It's physically rewarding, but in this case, it's intellectually rewarding. It's worth doing because in relation to the previous question, you may see something new. Okay, you may find a better way of doing it. It may be easier to lay down the next version as a result, but it's a very easy short-term fix. Again, human brain, we're really good at short-term stuff. Okay, we're very, very good at it, and our economics are often structured around that. So first of all, if there were an easy solution, I would not be here. I would be sitting in my yacht in the Caribbean. Trust me, I would have banked that solution a long time ago. But there isn't an easy solution. I'm afraid that part of it is hard work. But the first thing, as you recognize, mindset is important. The second thing is actually another aspect of the cutting back in order to grow. The ultimate cutting back is one thing that we're really quite difficult, we find very difficult, is called throwing away. Sometimes you look at that thing and go, that's perfectly elegant as a version of grep. If I'm going to make it much more complex, then I probably want to switch to a state machine. In other words, I need to throw the thing that I already had away, not add to it, not modify it, actually throw it away. Now, we have an interesting relationship with the idea of throwaway code. Has anybody ever used that phrase? This is just throwaway code. Yeah, it's actually quite common. And what's really funny about it is when you go back to somebody, oh, you know that throwaway code you wrote last year? Yeah, could I see it? Yeah, absolutely. Now, I want you to think about the metaphor. I set out at a ridiculously early hour to come to Israel on Monday morning from home, and I threw some stuff in the bin on Sunday. When I get home at the end of this week, when I get home, that stuff will be gone because I threw it away. And rubbish collection in my area will have gone by the time I get home. It will be thrown away. There is no getting it out. But in software, we've got this broken metaphor. It's never throw away. It's very, very rarely throw away. We're bad at throwing away. Let me show you this throwaway code that I've kept. I didn't really throw it away. That's just a bad metaphor. And so we're not very good at releasing things. Now, this is the interesting thing about making it small. If it's small and comprehensible and I understand it, I'm actually, if you take a step back, actually be easier to throw away than something that's large and I don't understand. That's one of our fears. That's why the wiki example worked so well. Ward didn't simply add to it, he rewrote it again and again and again because, oh, it's so simple, I understand what I want from it. The challenge there was not the body of the code. It wasn't a typing challenge, it was an intellectual challenge. It was a design challenge. Now, obviously you can't throw away 1,000,000 lines of code and expect to just recover the ideas. But if you make your 1,000,000 lines of code accessible in smaller parts, then it becomes easier. You don't feel as attached. You don't say, actually, well, let's throw that away. I've got a much better way of doing this. That thing that we had as a push, we're going to do it as a pull. That thing we had as a pull, we're going to do as a push. Oh, but that'll be a massive architectural change against the existing code. Yeah, but what if it weren't like that? In other words, it's often a series of asking questions. Again, that's not easy, but it's that beautiful piece of code may need to be thrown out. That's the hard bit. So the challenge here is, and I think the observation you made, I don't read these books because they frustrate me. Sometimes I get people telling me very, very similar things. I kind of look at it and it just makes me feel sad. Sometimes people feel angry, sometimes they feel sad because I go back to, I realize I can't do this at work. But what you've also said, you highlighted another point. Nobody said it would be easy, but I'm going to come back at you with one of my favorite quotes from a paper, Big Ball of Mud. People may have used the phrase, but the paper is worth reading by Joe Yoder and Brian Foote. And there's this beautiful phrase at the beginning, near the beginning, that says, if you think good architecture is expensive, try bad architecture. The point is, it's all going to be, it's that observation that all code is technical debt. It's all going to be hard. The question, your choice is not whether or not it's hard, it's how much hard, or how hard it is. Let's use some native English there. So how challenging it actually is. But you made another observation, which I think is really important. It's difficult to sell simplicity to colleagues. And unfortunately, this is the downside of the fact that we work... to managers, yeah, but I'm going to say it's all part of a collective group because they're part of the N. The management, the rest of the organization is part of the N when we talk about number of people involved. And that is the difficult bit, is the N allows us to do some things, collective intelligence. The problem is that it also works the other way, is sometimes that's our great weakness. Is the fact that if we cannot get collective intelligence, we have a bunch of individuals pulling in opposite directions. And that, I'm afraid, there's no magic solution to that. Again, yacht in the Caribbean, I would be there. But that is the idea that you've actually recognized what the essential issue is that, yeah, you can do it locally, but you're not going to get the global effect that you want because it's a whole, if the architecture is a reflection of the people that work on it, then it's a reflection of the people that work on it. And one person can make a bit of a difference, but, there's a limit there. So it does have to be a cultural change. The structure of the code reflects the company rather than the intended architecture, which sometimes leads to very frustrated architects wandering around. In fact, I've had this conversation with one person. They told me what the architecture was, and then I went and looked at the code with some of the developers, and I came back and I said, do you know that architecture you told me about? it looks completely different. Oh, well, they've got it wrong. The architecture is this. No, really, the architecture is that. It's in code, it runs, it executes, it makes money. So the difference is not whether it is the architecture or it isn't. It's whether it's the preferred architecture or not. And again, I'm going to go back to this idea that the architecture and the organization need to be sympathetic to one another. And that's the problem, is when we start overstaffing projects, when we have organizational structures interfering or poorly aligned because somebody made a logical partition, but that wasn't the way that the company was structured or the people were structured, then people will win. People will ultimately defeat the original design. And they will lay into it with pitchforks and burn it to the ground, and you'll end up with, well, whatever you end up with. And on that note, I will finish. Thank you very much.